Compton, right. Compton is the greatest cause of, occupational exposure, right, because of the high energy. Which interaction does not ionize an atom?
Coherent.
Coherent. Okay. Coherent. Okay. Which interaction with matter results in the production of X-ray photons in the patient's body?
Photoelectric?
Yep, you're looking right at it. Photoelectric. Okay. Photoelectric. Okay. So can you handle those three? Okay. All right. Now, pair production, you hit this, I guess, rather quickly, you said, with Ms. McNeila. And we're basically going to do that too. You do need to know some basic facts about it. Pair production does occur with extremely high energy photons. And when I say high energy photons, we're talking about greater or equal to 1.022 mega electron volts. To kind of put it into perspective, that's equal to 1,022 kilo electron volts. So in other words, the X-ray photons would have to have this much energy. Well, if my X-ray photons have this much energy, what would that mean as far as the kVp that I'm using?
It'd be very high.
Specifically what? What would it be?
I mean, close to 1022. It depends on the ripple, right?
Right. But yeah, the max energy would be, if my max energy is 1022 keV, that means I would have to be using a kVp that is 1022 kVp. Does our control panel go up to 1022 kVp? Now, what's the kVp range that I told you for our X-ray equipment?
Up to 150?
Yeah, like 40 kVp to 150 kVp. I am nowhere near this kVp. So our X-ray units cannot even generate these high energy photons. Okay. So these high energy photons, what they do is they'll interact with the electromagnetic field of the nucleus and get absorbed. Okay, so they'll interact with the electromagnetic field of the nucleus and they get absorbed. The energy gets converted into mass. See, unlike photoelectric, where even though the photon is absorbed, it knocks that inner shell electron out and that energy gets absorbed. Ultimately, we end up with an X-ray photon being produced, but, there is some heat that is transferred or generated within that atom as well. Here, what happens, the energy is so high, the energy gets converted literally into mass. We end up with two particles basically being produced when an X-ray interacts with the electromagnetic field of the nucleus. So the energy for that X-ray photon gets converted into a positron and an electron. So we end up with a positive charge being emitted and a negative charge being emitted from that atom. And the thing is, the electron and the positron have so much energy. The energy is so high that the electron can go on to ionize atoms. With photoelectric effect, the photoelectron can't. But the electron and the positron actually will ionize atoms. And then ultimately what happens is the positron and the electron will try to recombine. So they kind of crash into one another, and it's referred to as an annihilation event. Did you mention that term, annihilation event? Okay. Make sure you know very high energy. You do need to know that it's greater or equal to 1.022 mega electron volts. That's the energy of the photon you have to have. Make sure you know when the photon interacts with the nuclear field that the energy gets converted into a positron and an electron. And make sure you know that when the positron and electron try to recombine, it's referred to as an annihilation event. Because the positron and the electron, they get annihilated. So when they crash back into one another, the mass, the positron and electron, because they have mass, they get converted into two X-ray photons that are 180 degrees apart from one another. So we start out with very high energy photons. So we start out with a high energy photon. That high energy photon gets its energy converted into a positron and electron. The positron and electron collide in what we call an annihilation event, and the positron and the electron get converted back into a photon, but it gets converted into two X-ray photons that split the energy. See, 0.551 mega electron volts is half of this. So you start out with one photon, gets converted into two particles, those particles collide, and you end up with two photons that split that energy.
Is this what they're talking about when they talk about splitting the atom?
Kind of. Yeah. Yep. And this will occur in PET imaging. PET imaging. Remember what PET imaging stands for?
Positron something.
Yep. Positron emission tomography. Okay. Positron emission tomography. This is a fusion imaging. We talked just briefly about it, like the first day of class. It's a combination of CT and nuclear medicine. Okay, is what it is. And I don't know if you'll end up learning more about that in anything that Miss McNeila teaches you or not. I don't know if she goes into some of those modalities or not, but so this occurs in PET imaging. So we just don't see this in our area. Okay. I like the little cartoon here. I had to put that in there because I thought that was cute with the PET imaging. So dog ate the homework, but no, that's not what PET imaging refers to. You're not imaging your pet. It's the fusion of nuclear medicine, which shows the physiological processes taking place, and then CT, which shows anatomical structures. So it's a fusion of those two. Okay. So this is what it looks like. You know, this is, again, just kind of what I had the previous slide, kind of outlining the steps here. Interacts with the electromagnetic field of the nucleus. The energy gets converted into mass. And then that positron and that electron will end up joining together, annihilation event, and you end up with these two photons. So this is what it looks like. So a positron and the electron will collide, and here you get the two photons. So if you're asked on a test what interaction produces a positron and an electron, it would be what?
Pair production.
Pair production. And the name is a hint. Pair production meaning we have a pair of particles that are produced, and ultimately we end up with a pair of photons. So if you're asked what interaction produces two photons, each with 511 keVs worth of energy, that would be pair production. Okay. If you were asked about pair production and what imaging modality, what would you say? Would your answer be X-ray?
No, it would be CT and nuke med.
Okay, which would be what? You have to, because you can't just say CT and nuke med, because that makes it sound like it occurs in CT and it occurs in nuke med, but it's a fusion technology which we call
PET.
PET, right? Positron emission tomography, because it's a fusion of both of those modalities. Yes, so you would have to be specific and say PET imaging. Okay. And then the last one is photodisintegration. And you went over just some basics with this as well. And with this, you do need to know that this occurs with very high energy photons. So we're talking about 10 mega electron volts. So what keV would that be? On our control panel?
10,000.
Yeah, we're talking about over 10,000. So that is not on our control panel. So this is even higher than pair production, higher energy. Okay. Here, what happens is the photon actually interacts directly with the nucleus. So the nucleus becomes radioactive. The nucleus itself will release fragments. So we end up with neutrons, and we end up with protons, and even alpha particles. And we will not go into detail about, how this happens. That's something that, if you're interested in that and you want to learn more about that later on, there are plenty of sources out there that go into that detail. What you need to know for test purposes is, this number, and that it does actually occur with the nucleus. So nuclear fragments are released. Okay, nuclear fragments are released. In terms of medical imaging, this would be in the realm of radiation therapy. Okay, so this can occur in radiation therapy. All right, so that's all you need to know about it. That is it. All right. So can you think you can handle those interactions? Really, for the most part, that's just kind of memorizing what goes with what. Okay, what goes with what. If you're asked what interactions occur with photons with energies greater than 15 keV, what would you say? Photons, and we're talking about in our realm. You can always assume it's our realm. So greater than 15 keVs, what interactions?
Pair production.
Well, in diagnostic imaging, can occur with 15 keVs or greater and produce ionizations.
Compton scatter.
Compton and
Photoelectric.
Photoelectric. Right, Compton and photoelectric. Yep, okay. All right. So those are the interactions. Now terminology. X-rays that exit the tube, and I've mentioned this to you before, that's what we refer to as primary radiation or the primary beam, because those X-rays were formed at the anode, specifically at the actual focal spot, right? That's where X-rays are formed, is at the actual focal spot. So primary radiation is radiation that heads down towards the patient. That's our primary beam. Okay. Then we've got this other term, remnant radiation. It's also referred to as exit radiation. The remnant radiation or exit radiation, that is radiation that exits the patient. Okay. So the remnant beam consists of two things. It consists of X-rays that were transmitted, and it consists of X-rays that are scattered. So the remnant beam, the radiation that exits that patient and heads down towards the receptor, consists of transmitted and scattered photons. Transmitted and scattered. Okay. So we've looked at this, the transmitted and the attenuated, and what this means. Transmitted means what? What has that primary beam done? If it's transmitted, what is it doing? Has it undergone an interaction?
No, it has made it all the way through unscathed.
Unscathed, which is hard to believe, but it happens. So when you look at this diagram over here, what represents a transmitted photon? Let's number them. Like this is number 1, 2, 3, 4, 5. So what number?
2.
Number 2, transmitted. Notice there is no change in frequency or wavelength when it exits the patient. It was transmitted. Okay, this is part of the remnant beam. Attenuated means that, we have a reduction in number of photons as they travel through matter. So they've interacted. Okay, they've interacted. Attenuation can be absorption or it can be scatter. Absorption, what photon numbers would correspond to that?
1,
1,
3.
1 and 3. This one was absorbed by soft tissue. This one was absorbed by bone. Okay? So if it's been attenuated by absorption, it's not part of the remnant beam, right? Because if it's absorbed, it doesn't make it out of the patient. Okay? What interaction in matter is this attributed to? What's absorption?
Photoelectric.
That's photoelectric. Okay? Scattered. Well, which ones represent scatter?
4 and 5.
4 and 5. Technically, number 5 was attenuated because it doesn't make it to the image receptor, so it's no longer in the count. Because attenuation is a reduction in the number of photons as they pass through matter. So this one's gone. It exited out the side of the patient. Yeah, but that's scatter. That's been attenuated. Okay. This one too is also scatter, but it is part of the remnant beam because it exited the patient and it's making it down towards that image receptor. Okay. How do I know that this was scattered? How do I know? By looking at it.
Change direction and a higher wavelength, longer wavelength, less energy.
Yeah, there's a change in direction and it's got a longer wavelength, lower frequency. So I know it gave up some of its energy. Okay. So the transmitted photon and this scattered photon are part of the remnant beam. These X-rays are making it down to the image receptor and will interact with that image receptor. Okay. The absorbed photons are not part of the remnant beam because they're absorbed by the patient. They never make it out of that patient. Okay. So X-rays basically, can do 3 things. They can be transmitted, they can be absorbed, or they can be scattered. They can be scattered. You may be asked on a test, what does the remnant beam consist of? Scatter and transmitted X-rays. Okay.
Is scatter that makes it to the IR still considered to be attenuated because it lost some energy? Or is it only the number of photons?
Yeah, technically, and some sources sometimes will give you a little definition that's a little bit different. The definition that I learned and the one that I go with is if it's truly attenuated, it means it doesn't make it to the receptor. It's because attenuation means a reduction in the number of photons that make it to the receptor. So purely a numbers thing. So this one's been attenuated because it has not made it to the receptor. It's no longer in the count. Does that make sense?
Yeah.
Okay.
Can I ask you a question about scatter, which I think may be a silly question?
Yeah, sure.
I'm just trying to put this all together in my head. And I remember the experiment we did in the lab with the hand on the wall against the window. So with the scatter radiation, can you only get the scatter radiation if it goes through the patient first or image receptor first? I'm just trying to picture the scatter otherwise, maybe.
I'm not quite following what you're asking about the scatter.
It seems like the scatter is only after it interacts within the patient, correct? Or not the case?
Well, scatter can be produced by anything that the X-ray beam interacts with. The human body is considered to be the biggest attenuator because that's what we're imaging. And so we do get a lot of scatter being produced in the patient. But for example, if you have your let's say, for example, you have your collimation field opened wider than the image receptor. So that light field corresponds to the size of your X-ray beam, to the dimensions of your X-ray beam. So if you have a receptor, but you've got your X-ray beam open wider than that receptor, you can end up with some X-rays interacting with the table, and the tabletop can scatter X-ray photons too. Is that what you?
Yeah, so it does have to hit something. So like when we got the radiation exposure scatter from the phantom hand, it was because of whatever we were X-raying on the table.
Correct, because we had that X-ray beam directed at the abdomen, and so we had scatter being produced in that abdomen, and so a lot of that scatter exited, the sides of that abdomen, and were able to reach that image receptor and image the hand. Yep.
Okay, I got it. Thank you.
Yeah, you're welcome. Okay, and so the human body, in terms of composition, we're composed of bone, and we're composed of soft tissue, and these are all types of soft tissue structures. So when we say soft tissue, that means muscle and fat, blood vessels, tendons, ligaments, fascia. Well, all of this soft tissue gives us a very high water content, around 80%. This does vary from pediatrics to geriatrics, and it also does vary between males and females, but we typically say, around 80% or so water content. We do have water content in bone, but a bulk of the water content comes from all of these soft tissue structures. So our body's made up of bone, soft tissue, and then, of course, we have air also incorporated into our bodies. And when you look at what the body is composed of, that has an impact on whether or not attenuation occurs versus transmission. So what we are composed of has an impact on whether or not we end up with attenuation, which means either photoelectric absorption or Compton scatter, or pure transmission. So what we're made of is going to impact X-rays going straight through versus X-rays that undergo an interaction, either photoelectric or Compton. Okay. Now, when you look at attenuation versus transmission, three things will come into play. Okay, so there are three things that are going to impact how X-rays interact with the human body. So the first category deals with the composition of the anatomical structure in terms of the atomic number of that structure and mass density. Mass density has to do with how tightly packed the atoms are in that structure. Okay, how tightly packed. That's what mass density is. The unit of measurement is grams per centimeter cubed. So that's just how tightly packed are the atoms. So the anatomical structure will play a role. Tissue thickness is going to play a role in the amount of attenuation. And then the other thing that comes into play is going to be the X-ray beam itself, specifically the energy of the photons. So photon energy is going to play a role in whether or not we have an increased probability of transmission or attenuation taking place. Okay. All right, so let's look at these attenuation factors individually. So we'll look at atomic number, mass density, and tissue thickness. So the atomic number and mass density pertain to the composition of the anatomical structure. And this is something you're just going to have to look at, over and over again until you can kind of grasp this. With the atomic number, remember, atomic number is represented by the letter Z. As the atomic number of an element goes down, attenuation is going to go down, transmission is going to go up. And of course, the opposite is true. Atomic number goes up, greater chance for attenuation, less chance for transmission. Now, stop for a moment and think about it. Really, try to critically think about it and think logically. Why is this the case? You have to think about, what do you know about atomic number? And this is why we did, early on, we did a little bit with radiation concepts and talking about atomic number. What do you know about elements and their atomic number?
Increases absorption.
It can.
Just the binding energy is lower when the Z number is lower, and so it kind of takes less energy away from that photon when it has interactions, so it has a better chance of making it through.
Okay, it can. Even more basic than that, with the atomic number, what do we know about atomic number and the number of electrons? What's the relationship?
Oh, so like less electrons to interact with?
Exactly. With low atomic number structures, we know there are fewer electrons in the atom, right? Because as atomic number goes down, the number of electrons goes down. So if you have a lower atomic number structure, the probability of attenuation goes down because we've got fewer electrons that can be interacted with. So that means we have a greater chance of transmission. And then the opposite is true here. As atomic number goes up, we know we have more electrons in that element. So a greater chance for an interaction to occur. Okay, whether it be Compton or photoelectric, there's a greater chance for attenuation to occur because we've got more electrons there. So if we have a greater probability of an interaction, that means we have a lower probability for transmission. Does that make sense? Okay. Mass density has to do with how tightly packed are the atoms in that structure. Well, if we have a structure where the atoms are not very tightly packed, not very tightly packed, atoms aren't very tightly packed, what does that mean in terms of the number of electrons? Atoms aren't tightly packed compared to atoms being tightly packed.
And the attenuation has a less likely chance to interact with the electrons when they're spread out further.
Right, because we don't have as many electrons in a given area, right?
Like trying to get through a crowd of people.
Exactly. Like going to the mall at 8 or 10 in the morning on a weekday is a lot different than going to the mall during the holiday. You're more likely to run into more people because the density, people are more tightly packed into a store than what they are, first thing in the morning during a weekday, during a non-holiday type of season. So the same things here. When you decrease the mass density, there are fewer electrons, so the probability of attenuation goes down, probability of transmission goes up. And then the opposite is true here. The more tightly packed you have the atoms, then the greater the chances are that we're going to have an interaction. And the less likely will be the chances for transmission. Okay? Does that make sense? Okay. Tissue thickness, the thickness of the part. As the thickness goes down, we're going to decrease the chances that an interaction will occur, which means our transmission will go up. As that part thickness increases, there's more there. So greater chance for attenuation, but less transmission. So do you follow that? And then the last factor that impacts attenuation versus transmission is the photon energy. So the three factors here all pertain to the anatomical structure. Now, these two have to do with the anatomical composition. This has to do with the thickness of the anatomical part. And then this one here is an X-ray beam characteristic. So your photon energy is going to play a role in the likelihood of transmission versus attenuation. If the energy of the photon is lower, so we have lower KeV, lower energy, we have a greater chance for attenuation to occur. Greater chance for attenuation, lower chance for transmission. Okay, lower chance for transmission. As the photon energy goes up, we're going to decrease the chances that it's going to interact with an electron. It's just going to blow right by the atoms. So a greater chance for transmission to happen as the KeV of the photon is higher. Right? So less likely to undergo interactions at a higher KeV. Much more likely to make it through without hitting any atoms at all when it has high energy. Okay. So you okay with those attenuation factors? All right. All right, let me see. We have, hold on a second. Let me go back to that. These examples. Okay, I'll tell you what. Atomic number, mass density. All right, I'll tell you what. What's on your test on Wednesday? What's your test cover?
Everything we need to know for the quiz plus today.
X-ray.
Half of X-ray production, right? Where we started talking about all those specifics with the anode line, focus principle, anode heel effect, all that type of stuff. Right. Through today. So you've got X-ray production, you've got prime factors as well, right? Okay. All right. How about as far as today's material, why don't we have the test go through interactions? So the 5 interactions. Okay. So the last few slides that we talked about where we were looking at the probability of transmission versus attenuation, talking about mass density, atomic number, thickness of the part, and photon energy. We'll save that for the final, okay?
So would you say through slide 16?
Whatever that number is, where we end with, I'll tell you what. You need to know, I'll tell you, through slide 16, because, we've talked about this before, transmitted, attenuated. So, through 16. Yeah,